The digital ecosystem runs on a continuous, mechanical pursuit of silence. In information theory, silence means one specific thing: the algorithmic eradication of data redundancy. The modern rules for achieving that silence were established in 1948. At the Massachusetts Institute of Technology, Claude Shannon and Robert Fano began searching for a practical way to represent any discrete set of data using the most compact binary code possible. Shannon had already calculated a precise mathematical boundary called entropy. Entropy dictates the absolute theoretical limit of data compression based entirely on the predictability of the source material. To hit that limit, Shannon and Fano developed a top-down, greedy algorithm. They ordered data symbols by how frequently they occurred, and repeatedly sliced that list down the middle, trying to keep the cumulative probabilities in each half as equal as possible. One half was assigned a binary 0, the other a 1. The logic was straightforward. But mathematically, it failed. Because the probability masses rarely divided perfectly evenly, the terminal ends of the tree splintered into fractional imbalances. The code it produced carried structural redundancy. Shannon and Fano could prove their method was mathematically imperfect, but they could not find the formula to correct it. The creators of information theory were stalled, unable to write an algorithm that matched their own theoretical limit. By the autumn of 1951, Professor Fano was still stumped. While teaching the graduate course, he offered his students a choice: sit for a standard final exam, or write a term paper solving the most efficient method of binary coding. He deliberately omitted the fact that he and Shannon had been failing to solve this exact problem for years. A 25-year-old student named David A. Huffman took the term paper to avoid the exam. For months, he drew complex tables and branching directed graphs. As the deadline approached, he still couldn't prove any of his codes were optimal. Terrified of failing the class, he gathered his notes, threw them into the wastebasket, and decided to start studying for the final. Looking down into the trash, Huffman saw his discarded tree structures sitting upside down. The change in perspective shifted the entire methodology. The problem couldn't be solved by splitting a whole into parts from the top down. It had to be built from the bottom up. Huffman retrieved his notes and applied a greedy mathematical logic. He made every single symbol a disconnected leaf node. Then he took the two symbols with the absolute lowest probabilities and merged them together to create a new parent node. He repeated this exact process, merging the lowest values until only a single root node remained. By forcing the least frequent symbols to merge early at the bottom, they were naturally pushed deepest into the tree, requiring the longest binary sequences. Statistically frequent symbols merged late, staying near the top, receiving the shortest sequences. The math was airtight. For a highly skewed probability dataset, Shannon-Fano's top-down method yielded an average length of 2.0 bits. Huffman's bottom-up method hit an average length of 1.95 bits. When Huffman handed in his paper, Professor Fano was reportedly in shock. A graduate student had bypassed the mental roadblock of his professors, engineering a provably optimal framework for symbol-by-symbol prefix coding. To understand the ceiling of Huffman's algorithm, you have to look at how hardware actually reads a continuous stream of ones and zeros. A computer doesn't have spaces or commas to tell it where one character ends and the next begins. It requires a prefix-free code, where no sequence representing a symbol can serve as the prefix for another. The physical space to create these non-overlapping prefixes is strictly bounded by a mathematical principle known as Craft's inequality. You only have so much binary space to pack in your alphabet before you run out of unique paths. Huffman coding uses that available space perfectly, but it contains a fatal mathematical ceiling. It is forced to emit discrete integers. If a symbol's probability dictates it should ideally take up exactly 1.6 bits of space, Huffman can't output a fraction. It has to assign either a 1-bit or a 2-bit code, instantly introducing fractional redundancy. This bar chart contrasts the theoretical limit of Shannon entropy against the physical floor imposed by Huffman coding. Consider a highly skewed data stream where a single symbol occurs 99% of the time. The mathematical entropy for that symbol is roughly 0.08 bits. Because Huffman must assign at least one whole physical bit to every symbol, it is stuck at 1.0. It operates at 12 times the theoretical minimum, hemorrhaging storage capacity. By the 1980s, engineers developed arithmetic coding. Instead of rigid whole bit codes, It encodes an entire message into a single, precise fractional number between 0 and 1. It effortlessly absorbs fractional bits. In empirical tests on standard JPEG document scans, arithmetic coding reduced file sizes by over 70% compared to heavily optimized Huffman encoding. From a strictly mathematical standpoint, Huffman coding was obsolete. It could not compete with the fractional precision of arithmetic encoding. Yet the digital ecosystem firmly rejected the superior math. The reason was entirely legal. Throughout the 80s and 90s, international conglomerates like IBM and AT&T filed sweeping patents covering virtually all practical implementations of arithmetic coding. Open standard development ground to a halt. When the Joint Photographic Experts Group finalized the JPEG standard, the consortium explicitly stripped arithmetic coding from their free software distribution. They warned developers that using the superior code without commercial licenses risked severe litigation. This threat created the Huffman Moat. Software ecosystems, operating systems, and web browsers universally defaulted to Huffman coding. Mathematically suboptimal compression was accepted worldwide as the necessary price for legal safety. But surviving as the default meant engineers had to armor the algorithm. Standard Huffman trees are notoriously inefficient to process in hardware. Storing the distinct left and right child pointers in system memory consumes massive amounts of RAM. Decoding requires bit-by-bit traversal, triggering cache misses that stall CPU execution pipelines. To solve this, computer scientists introduced canonical Huffman coding. By applying a strict, deterministic lexicographical sorting to the symbols, the literal tree structure is completely eliminated. The codebook can be perfectly reconstructed purely through sequential arithmetic. Software can execute fast table lookups instead of blindly navigating a linked list in memory. This speed was then fused with a spatial compression technique called LZ77. A developer named Phil Katz engineered DEFLATE, an architecture that uses LZ77 to strip out spatial string repetition, and then immediately feeds that raw data into canonical Huffman sorting to eradicate symbol frequency redundancy. DEFLATE became the core of the zip file format and the PNG image standard. Huffman's algorithm became the indestructible backbone of the internet, surviving not for its perfect math, but because open-source resilience armored it against corporate monopolies. For 70 years, engineers had to choose between the legal safety and execution speed of Huffman coding, or the fractional density of arithmetic coding. In the early 2010s, a Polish academic named Dr. Jarek Duda eliminated the choice by inventing asymmetric numeral systems, or ANS. ANS discards both older methods. Instead of dealing with discrete binary strings or narrowing fractional intervals, ANS encodes a continuous stream of information into a single, ever-growing natural integer. As new symbols arrive, the state integer grows precisely and proportionally according to the symbol's exact Shannon entropy. To make this viable for hardware, Duda created a tabled variant, TANS. He collapsed the complex math into pre-computed state machine arrays. A software decoder simply checks the table to find the decoded symbol and the next integer. It executes at speeds matching canonical Huffman, while maintaining the fractional bit density of arithmetic coding. The results broke the historical trade-off. Integrated into Facebook's open-source Z-standard algorithm, ANS allowed datasets to be compressed at over 500 megabytes per second and decompressed at over 1,500 megabytes per second, thoroughly outclassing legacy Huffman formats like gzip in both speed and size simultaneously. Intensely aware of the damage caused by the IBM patents in the 90s, Dr. Duda intentionally published the exact mathematics of ANS directly into the public domain. Despite this, in 2017, Google filed a broad application in over 100 countries to patent a specific hardware application of ANS for video compression. Duda filed aggressive formal protests with the World Intellectual Property Organization, pointing out that he had personally explained the math to Google engineers on public forums over the preceding 3 years. Google claimed the patent reflected novel hardware applications and would be licensed royalty-free. The controversy exposed the immense, hidden commercial leverage embedded in fundamental data constraints and the persistent hostility between public academic research and corporate intellectual property capture. After leaving MIT, David Huffman moved to UC Santa Cruz to help found its computer science department. By the 1970s, his intellectual focus pivoted away from digital engineering to a highly physical manifestation of mathematical constraints. He became a global pioneer in computational origami, specifically focusing on the complex topology of curved crease folding and zero curvature surfaces. Huffman mapped out the meticulous differential geometry required to manipulate rigid paper into complex three-dimensional sculptured shapes without cutting, tearing, or stretching the physical material in any way. The connection between his algorithm and his paper art is precise. Both rely on navigating absolute limits. His digital compression sought to pack maximum informational meaning into a strictly confined physical binary space. His origami forced a physical sheet of paper into highly ordered structural shapes, subject to unyielding material rules. His physical fold models heavily influenced structural architecture and mechanical engineering, demonstrating that the equations governing digital data and the physical laws of spatial geometry share a universal kinship. ANS has finally evolved data compression beyond the confines of the classic binary tree, but the foundational logic of the merge remains. Whether structuring a bit stream or calculating the geometry of a curved crease, Huffman's work remains the proof that the most efficient structures are found by recognizing the unyielding constraints of a system and building upward from the absolute bottom to find the shape within them.